Anyway, ooh. Good morning, people. Let's go ahead and get started. Moving on here. So we're going to continue with the same thing. So the objectives are going to be the same. Find the value of given inputs for greatest value functions and greatest value and graphing greatest value functions. So imagine if you had Trifiddy. How many hot and spicy sandwiches could you buy? So if I ask you this, you probably already know the answer, but then if you were going to try to do this mathematically, you might say, okay, well, let's see. A hot and spicy is about $1.08, and X is the number of hot and spicies that you can buy. So if I divide both sides by $1.08, that'll give me exactly how much I need to buy. And if I got a calculator and I were to divide Trifiddy by $1.08, it says here that I could buy 3.24. And I'm sure you've been to McDonald's a few times. Can you buy a quarter of a hot and spicy? You know, if you were to beg the cashier, be like, please, I need a quarter of a hot and spicy. You know, just cut it in half and cut it in half again and give me one of those pieces. No, they're not going to do that. They're not going to serve you that type of service, because they only sell whole sandwiches and they're only going to sell it to you for a whole price, and the price is already pretty low. So why would they want to have it sold for any less? So this is the kind of problem that we're going to be working with today, because you really, again, you can't buy a quarter of a sandwich. So realistically, you would buy 3 of them would be the maximum number of sandwiches you could buy. So that's the greatest value function, and that's going to be, greatest integer function. Anyway, so we write it like this: f of x equals, and we have this double bar bracket here. And that just means, again, that essentially it's like a rounding down symbol. I mean, if you had like $1.05, and you wanted to buy, the sandwich, they probably still wouldn't sell it to you. They probably say, nope, $1.08, and that's it. Take it or leave it. So again, you can think of it kind of like a rounding down, whereas like normal rounding, if it's 0.5 or higher, then you round it up. If it's lower than 0.5, or the next, like if you in the place value, the next place value lower is 5 or lower, then you round it down. Okay, so it's not like that. In this case, it's always round down. And that symbol means basically the greatest integer less than or equal to x. So, or equal to. So again, if you had exactly $1.08 in your pocket, you could buy the sandwich. Because, I mean, you'd spend all the money you had on you, but you would still get the sandwich. So basically, it means that you round it down. And then, yeah, they call it the floor function, which I don't remember, but I think I don't know, there's another symbol that kind of looks like that, and that also means the same thing, round down. Anyway, let's go ahead and go for the first one. So find the given f of x. We got to find the value of each of these. Let's see, I'm going to use purple today. So if I put 7 in here, remember, it's got to be the greatest integer less than or equal to that number. But in this case, we actually have it equal. So 7 is equal to the closest integer because it is 7. 7 is an integer. So f of 7 in this function just comes out to be 7. All right, so here we have a decimal. So this one's not an integer. Since it's not an integer, we might have to do some work on this one here. So for this one here, again, round it down. So 2.3, round that down to the nearest integer, you're going to get 2. So it's going down. And for this last one here, C, we have a negative number, negative 4.8. So negative 4.8. Now round that down. Think about it. If you were looking at a number line, so in a number line, you get like, if you imagine 0 in the middle, negative 10 on this side, and positive 10 on this side. Rounding down would actually mean that you'd have to go deeper into the negative, up in the negative value, which you'd still be going towards the lesser sign. Remember, there's a right is greater and left is lesser. So you'd still be going to the left. So in this case here, the function of greatest value integer of negative 4.8, oops, almost forgot the negative. Negative 4.8, that would come out to negative 5. And there we go. So now we have another one. So x minus 5. So what we're going to do is we're going to place 9 in here. So 9 is x. So 9 minus 5 would be 4. And then we have to round that down, which again, it is already an integer. So it just stays 4 because again, less than or equal to that number. So in this case here, f of 9 equals 4. And f of 0.5, so here I have 0.5 minus 5, and that would be negative 4.5. And we have to round negative 4.5 down, so that would be negative 5. And negative 8.1. So if you imagine a number line in this case here, so I have negative 8 and negative 9. And again, normally negative 8.1 would be really close to 8. Okay, it'd be something like right there. But we round it down, even though it's closer to this number, we always round it down. So, oh wait, we got to plug it in. So negative 8.1 minus 5. So we'd actually have to go down a little bit. And just to make sure I get this right, well, actually I can't. I can't really do negatives with this. So I'm going to use this one. So we get 13.1. 13.1 negative. And we have to round that down. Rounding down negative 13.1, we would get negative 14. So after we do the minus 5, then we have to check and round it downwards to the nearest whole number, nearest integer. Well, it is kind of like whole number, but integers can also be negative as well. And again, not that bad, not that tough. All right, I already filled out these numbers here. So if you need to, go ahead and fill those numbers in. So we're going to get a table here and graph the function and then to identify the domain and range. So we have the very basic function, like the parent function. Again, it's just really, really basic. All right, just to mainly give us an idea of what we're trying to get. So we got 0, and we round that down. So rounding 0 down to the nearest integer would be 0. So again, I use the example of the dollar sandwiches. So for this one, let's ignore the tax, okay? Ignore the tax. So if it says dollar sandwich, it will cost $1, all right? Maybe we're in an area that there is no tax, or the tax is already factored into the price. So that actually sounds like a really good place to live. You know, you just pay the sticker price and that's it. Anyway, so if we're trying to buy a $1 sandwich and we have 25 cents, you can buy 0 sandwiches. If we have 50 cents, all right, and again, no matter how much we ask the cashier, they're not going to cut a sandwich in half and sell it to us for half price. Okay. I don't care how smooth you think you are. 0.75, round that down. If you had 75 cents, nope, still not going to sell you the sandwich or the bag of Cheetos or whatever you can think of that's $1. But if you had exactly $1, yeah, you can buy one. Or maybe you're buying something from a personal vendor, you know, maybe not like a store, maybe not like a Chevron or a 7-Eleven. Maybe you're buying something from a flea market or something, you know, and it's like $1, and people at those sort of places don't usually charge taxes. Anyway, back to here. So if you had $1.50, how many of those things could you buy? Well, you can only buy one of those things, because the 50 cents doesn't really do anything. You know, you're just going to end up leaving with it in your pocket still. If you had $2, you could buy 2 of them. If you had $3, you could buy 3 of them and 4. And if you know, this pattern is basically going to continue. So if I had like $3.50, well, I'd probably be the Loch Ness Monster, but I would also be able to only buy 3 of those items. So you end up with something that the graph is going to look a little bit weird, because at 0, it would look something like this. I'd have a line right here. So between 0 and y being 0, and 0.25 is like right there, half is right there, and 0.75 is right there. And they're all on the same line like that. And now we need to cap it off. So in this case here, if you imagine that if you had 99 cents, right, and you're just like 1 penny short, I don't know, maybe if it was just 1 penny, maybe the guy would be nice to you and let you have it for 99 cents. But let's say he's really, really strict and he says, nope, must be $1. If you had 99 cents, no sale. But if you had walked outside and found a penny, then you would be able to get one. So up 1, or sorry, X is 1, so over 1, up 1. So that's the ordered pair right there. And this pattern kind of continues again. Once we get to 2, so over 2, up 2, so we're going to graph this part here, over 2, up 2. We go through that little hoop and we reach this area here. So if I had $2, I could buy 2 of them. And again, if I had $2.99, no dice. If I had $3, I would be able to buy a 3rd one. And maybe I'm trying to buy as many of these as I can. But in a way, this is a little bit more realistic, a little bit more lifelike than, you know, a line graph, because a line graph would imply that you could buy, you know, 25 or 50 cents worth of a sandwich, and that's just not possible. You know, I don't think anybody's really ever done that. And I'm talking like regular stores, okay? Maybe your uncle did sell your dad, you know, 2 tires from his old Ford one time, or sold a part of something. And this pattern just continues exactly in the opposite direction for negative numbers as well. Now we run into the problem of the domain and range. So what is the domain of this? Now in this case here, we do have the ability to pick all real numbers. Because if we pass a vertical line slowly through this whole thing, right, we're able to touch these purple lines at least in one place the entire time. However, for the range, we have a bit of another problem, because if I pick something like, I'll go with $3.50 again, or $2.50. If I pick $2.50, I cannot buy $2.50 worth of dollar items. So there's no way I can have an output that is $2.50. And really no amount of cents, anywhere between 1 cent and 99 cents isn't gonna help. So in this case here, only integers, meaning that it has to be a whole number, whether it's negative or positive, it has to be an integer. And that's it for the first one. Now we're gonna have to do a little bit of work because we don't have that many more. We only got like 4 examples. And I looked at the homework, there's only like 1 or 2 of these problems, so it's really not that much. But it's always a good thing to cover these things. Okay, anyway, moving on. I got the numbers already filled in here, so that way at least we, again, can get a pretty good idea of where the function is, you know, what it looks like. Okay, same directions, get the pattern, graph it, identify domain and range. Now with this one, it's a little bit different. Because the minus is on the outside. So this means that we have to round it down and then subtract 5. So 0, okay, so 0 minus 5. Okay, 0 is already an integer, so 0 minus 5 is going to be negative 5. 0.5, now again, we got to put it in here and round it down first. So 0.5 rounded down is going to be, well, 0. Now again, this is different than normal rounding because in normal rounding, if it's 0.5 or higher, you round it up. But always round down. Okay, always round it down. So in this case, it would be 0 minus 5. So you get minus 5 again. And then 1, so let's go ahead and put 1 in there. 1 is already an integer, so we don't need to round it. 1 minus 5 is negative 4. And 1.5, put that in there and round it down. So again, it's not typical rounding, so we're gonna have to always round it down, so that would be 1. And 1 minus 5 is negative 4. Now we have whole numbers. So these are just here to help us establish the pattern. These are already integers, so it's just 2 minus 5, which is negative 3. 3 is already an integer, so 3 minus 5 is negative 2. 4 minus 5 is negative 1. So let's go ahead and plug these in. So at x is 0, that would be minus 5, so that'd be like way down here. And at 0.5, it's still negative 5. And again, this is true from 0 to 0.99. All right. And we have an open end on this side because now we've reached the next integer. So it should be right here. And let's test that out. So there's the x-axis, go over 1, down 4. And that's exactly where the ordered pair for the next one starts. Over 1, down 4. And it still gives us a half number, so 1.5 on the x-axis. 1.5 is right there. If I were to go down, I should still be on that same line, which is true. And again, it goes all the way down to basically 0.99. And we now have our pattern basically, and it's always going to be this, they look like steps, okay? They look like little stairs. And I think that these are actually also called step functions as well. I don't know why they didn't call them step functions in this case. I might be wrong and it might be something a little bit different. But anyway, yeah, I would look something like that. There'd probably also be one more dot. So like a step function or steps, you know, if you're stepping on these things, you got to be on one or the other. And you almost never put your foot like right there underneath the next one, or maybe you do. Anyway, back to the domain and range, and domain is going to be, again, all real numbers. So everything's covered. These lines go forever in both directions. All right, so if you were, now this is not a really good example for the hot and spices, but if you were thinking back at the other one, you know, you could buy a ton of hot and spices. Like if you called a McDonald's ahead of time and you said, I'm putting on a party, I need like 500 hot and spices, they probably would do it for you. So you could order any number of them as long as you got the money. And range is kind of the same thing. We got integers. Integers, again, meaning like a whole number, whether it's negative or positive. So we can't pick any numbers on the y-axis between these numbers. We can only pick them on these grid lines. So -1, -2, -3, -4, -5. Those are the only ones we can pick that we can see. And again, this pattern goes on and on forever. So we got to make sure we have this sort of step function go, you know, go up. Okay, so let's go ahead and move on to the next one. So for this one here, I have x, and I'm going to use these numbers to plug into here. So I don't know if I should write these out. Maybe if I wrote them out, then it would be a little bit of work. So you're just going to have to kind of follow me. But you could probably also write these down. Maybe I'll write out the first few of them. So 2x, so 0 minus 1. So 0 minus 1 is going to be -1. So 2 times -1. Oh, wait, hold on. That's not, okay, so that's not really a bracket the same way that you've seen other brackets. So sometimes in order of operations, now you should put these little double lines on there because that tells you that it's the rounding down function rather than the other one. So again, it's a little bit confusing, I know. But if I round it down, I would get 2. And if I round -1 down, it would be -1. And it just sort of becomes regular parentheses in this case. So 2 times -1 is -2. And again, once we get the pattern, once we kind of understand where the steps are going to be, it's a little bit easier because we don't need to worry too much about exactly where each of them is going to be. We just got to keep following that pattern. So let's go ahead and do the same thing here. So 2 and 0.5 minus 1. 2, and then let's see, 0.5 minus 1 is going to be -0.5. And this is still kind of a multiplication symbol. Still multiplication. Because anytime you put two numbers directly next to each other, that means that you're going to multiply them. But in this case here, I'm going to round it down. So round down 0.5, and you get -1. And that means this is still -2. Okay, now for this one here, I'm going to put 1 in here. So imagine that this is 1. I only have enough space to write one more, and I'm going to save it for this one. So I'm going to put 1 minus 1, and we get 0. 2 times 0 is 0. And like I said, that one's just basic math. Just grab 1, put it in here. 1 minus 1 is 0. 2 times 0. Let's try this one with 1.5. 1.5 minus 1. Okay, so 1.5 minus 1 is going to be 0.5. And we round that down. Rounding this down, we get 0. And again, it's still a multiplication symbol. It's still a bracket like the regular kind. So yeah, that's probably why I confused it with the other one earlier, just by looks alone. 2 times 0 in this case would be 0. And now we just do the rest for each of these. So again, this should be enough to help us get our pattern, but let's finish these. 2 minus 1 is 1, which is already an integer. 2 times, well, 1 times 2 is 2, or 2 times 1, whichever one works better for you. 3 minus 1, so 3 minus 1. 3 minus 1 is 2, and that means 2 times 2 is 4. Plug in 4 for x. 4 minus 1 is 3, and 3 times 2 is 6. So now we have our table filled out. Let's go ahead and graph these points. So at 0, we go down 2, and we have a spot on the graph right there. And 0.5, so again, 0.5 on the x-axis is right here. So if I go directly below that, it's still at 2. And it's going to stay that way all the way until 1, because if I go over 1 for this third number here, that is going to be another point on our graph. And I don't really need this. I was just showing where 0.5 would be. And that would mean that we'd have an open circle under here, because again, in order to be a function, it has to pass the vertical line test. And if I have 2 spots where that vertical line can cover, then it's not a function. So this has to be a function. And let's see, if I were to go over 1.5, which is right here on the x-axis, I would still be at 0. Over 2 up to, and let's see, 3. So if I go over 3, I have to go up 4. And if I go over 4, I have to go up 6, which would be up here, but that's off the graph, so we don't need to graph it. Now, just for consistency's sake, I'm going to go ahead and fill in this back area up here. So we kind of end up with this vertical stretch of numbers. So it's like stairs, but you're stretching them upwards. So I remember during the transformations, actually, I think, okay, well, it hasn't happened. If you're watching this on the video, it hasn't happened yet. But in transformations, we talk about vertical stretch, which means, again, you grab the top and bottom and you pull the function like this so that it kind of stretches upwards. So if you imagine writing it on a piece of paper that's kind of like rubbery where it's stretchable, you would have that stretched. So I sometimes get the question of, what about horizontal stretch? Is horizontal stretch a thing? And usually not quite, because in that case, it would be a vertical compression. So it's kind of like, again, making your stairs up higher. So it's kind of like a ladder, not like stairs. Because if you had really steep stairs, you know, that's not good. I saw these places in like China, or I don't know, it might be somewhere else in Asia. But they have these temples that the stairs are really, really steep. Kind of what it reminds me of. Anyway, last one. So here we have a 1/2 number. So we'll see what this one does to this. A 1/2. So let's go ahead and plug in. Oh, let's see, maybe we could multiply this like this. So 1/2 times 0, because we're going to use this first spot here. So plug in 0 where x is. And 0 times half, well, anything times 0 is 0. So this means that this first number is going to be 4. All right, let's go ahead and do this one here. So we get half. Now that's already an integer, so we don't need to round it. Half times 0.5. half times 0.5. So that would be, well, a quarter. And that would be 4.25 because this is half of half. So half of 0.5 is 4.25, or sorry, after I add 4 to it, it'd be 4.25, but it would be just 0.25 here. And it's got these things here, so I'm gonna have to round it down. So that would be 4. All right, let's go ahead and plug in 1. Now this should be an easy one because 1 times 1 is just 1 times anything is going to be that same number. So half of 1, so that'd be 0.5 plus 4, so that'd be 4.5. And if I were to round that, it would be 4, so we get another 4. And now time for this one. So half of 1.5 plus 4. And if you think about it, what's half of $1.50? Well, okay, so in that case, you probably figured out pretty easily. It's about 0.75. So in this case, we get 4.75 if I add that, but I still have to round it down. Even though it's close to 5, we always round it down, so that'd be 4 as well. All right, what about 2? Now I'm out of space to write this out, so we're just gonna have you follow along. 2 times half, or half of 2. So if I take half of 2, that'd be 1. And 1 plus 4 is 5. So again, plug 2 in here. Half of 2 is 1. 1 plus 4 is 5. And it's already an integer, so I can't round it down. And let's go ahead and go with 3. So I'm going to plug 3 in there. What's half of 3? That'd be like 1.5. So that'd be 1.5 plus 4, which would be 5.5. Take 5.5, round it down, and you would get 5. And 4, you know, we didn't even do the domain and range on this one. Oh boy. I just noticed that we didn't. I was like, wait a minute, did we? Okay. Anyway, let's continue here. 4, and we take half of that, that'd be 2, right? Because half of 4 is 2. 2 plus 4 is 6. And we round that down, it would be 6. Now, before I go on, I'm going to go finish the domain and range on this one. I don't know how the heck I missed it. But domain, all reals. And the range would be even numbers. So pretty much any number as long as it's even. Okay, back to the other one. So we got to graph this one here. And I get 0 and 4, so 0, 4, 0, 4. And let's see, 0.5 is also 4. 1 is also 4. 1.5, so that's over here. And that'd be up 4. And 2, so this one's going to be 5, so over 2 up 5. So it looks like our graph is going to look something like this. And we don't have a lot to go on, but just sort of keeping our pattern the same. We're just going to have to work backwards from here. So it looks like we are would look something like that. Okay, now let's not forget the domain and range on this one here. So domain would be all real numbers. And even though there is a bit of compression going on here, it doesn't really affect the range any different than a lot of the other kind of problems. So it would still be integers. So if I'm looking at the y values, starting from the lowest one that I can see, it looks like 1, 2, 3, 4, 5. So it's all the regular numbers. And if I kept going back this way, you know, if I kept going this way, it would be going down, and it would just continue that way. You would get numbers just headed off this way and that way. I wonder if, let me check something really quick. I wonder if Desmos has this function. I never checked it, but I wonder if it does, because I've never looked for it. But it would be kind of interesting to see that if it does or not. And it looks like it does. So I'm going to go ahead and just jump over there really quickly. So I just punched it in, and it looks something like this, although they call it a different name. They call it floor. And let's see, but this one is kind of a weird one because it doesn't stop right at 1. And here I'm able to pick the same spot in both of them. So I don't know if I'm picking the wrong function. And I don't see the sign that they gave us. But it looks like you would still be able to do the same thing that we did on the other one. So if I minus 5 from the function, so go to this, minus 5. Now it looks like it's kind of shifting over, but it's actually gone down. So the whole graph, rather than, again, going like this, is actually going down. And I could also move it over a little bit more by doing something like minusing 4. It looks like it's actually going back the other way, but actually that's not what's going on. And let's see if I don't know if I can times this by half. Oh, there we go. So now it's kind of like stretched sideways. Or if I were going to do it this way, it would be stretched the other way. So yeah, it seems to behave the same, but they call it a different name. And for some reason, I don't know if this is an error in the graph, but I should not be able to pick the very next number. Or maybe it's not. Maybe it's not letting me pick that next number. 0.9964, 998. Slowly, slowly, slowly. All right, I'm getting really, really close, but it's not letting me pick the next number. So okay, so maybe this is the right function type that we're looking at. Anyway, yeah, but they just seem to call it floor instead. All right, so I guess that's it for today. I'll be around if there's any more questions. Now, remember, this week is the last week of the quarter, so I've been helping some people afterwards. I've been actually helping a lot more people than I normally do because, again, you got to get your packets in. So if you have any more questions, I'll be around for as long as I need to answer them. You know, we can go over any of the problems in any of the other packets, or if you're missing notes or something like that, we can go ahead and cover that. I'll be around until everyone's gone, but that's it for today's lesson. And I told you it'd be a little bit shorter than the usual one. Make sure you get your week 1 through 7 packets in. And that's it for today. I'll see you tomorrow. Bye-bye.